There's a gas that costs $1 and keeps any tire at its correct inflation pressure for months instead of weeks. Not slows the pressure loss slightly. Reduces monthly pressure loss by over 80%. A tire filled with this gas that loses 10 psi per month with normal air loses less than 2 psi per month. You check it twice a year instead of every 2 weeks. You never add air between annual inspections. You never find a tire dangerously underinflated because you forgot the last time you checked it. Your fuel economy stays at its calculated optimum because your tires maintain the rolling resistance your vehicle was designed around. Your tires wear evenly because the sidewall flex characteristics your engineer specified are maintained continuously, rather than fluctuating between inflated and underinflated states every cycle of your neglect schedule. Formula One racing teams use this gas in every tire on every car at every race weekend. Commercial aviation uses it in every aircraft tire on every commercial flight worldwide. The United States military uses it in the tires of every combat vehicle from Humvees to Abrams tanks. NASA uses it in spacecraft launch vehicle tires. Every tire-intensive application where inflation stability is safety critical uses this gas. And the automotive industry that sells you replacement tires every 3 to 5 years, due in part to uneven wear from chronic underinflation, and the tire service industry that charges $5 to $10 per tire to fill them with the same gas that racing teams use for free, has spent decades making sure that the average car owner associates this technology with Formula One and not with their own driveway. The gas is nitrogen, the same nitrogen that fills 78% of every breath you take. The same nitrogen we discussed in the food preservation vault filling storage containers to keep grain fresh for 10 years. The same inert, abundant commodity gas available from welding suppliers for $1 per cubic foot. But in tire service shops, it is sold as a premium nitrogen tire inflation service at $5 to $10 per tire, packaged as specialty automotive technology requiring professional equipment, when the physics is something any high school chemistry student knows. This is the story of the atmospheric science that aerospace engineers applied to tires in the 1950s, and that the industry repackaged in the 1990s. Welcome to Forbidden Camping. Subscribe and hit the bell right now. This channel opens the vaults they spent decades locking. Now let me take you back to where this all begins. Let me take you back to 1956 at the Goodyear Tire and Rubber Company's research facility in Akron, Ohio. Goodyear's engineering team is working on tire compounds and inflation specifications for a new generation of commercial aircraft tires. These will be used on the Boeing 707, the first American commercial jet airliner scheduled to enter service in 1958. Commercial jet aircraft present tire engineering challenges that ground vehicle applications had never required solving at that scale. An aircraft tire experiences landing loads of several 100,000 pounds and decelerates from landing speed to 0 in seconds. The pressure and temperature cycling that occurs across a landing event is extreme, and aircraft tires cannot lose inflation pressure unpredictably. An underinflated aircraft tire on a landing gear fails catastrophically rather than just wearing unevenly. The Goodyear engineers, testing different inflation media, discover that tires inflated with dry nitrogen show dramatically different pressure retention characteristics. A tire inflated with nitrogen loses pressure at approximately 1/5 the rate of an identical tire inflated with compressed air. The reason is not mysterious. It is atmospheric science documented in every chemistry textbook. Nitrogen molecules are larger than oxygen molecules and do not permeate rubber polymer at the same rate. Oxygen, at 0.346 nanometers, diffuses through the rubber wall faster than nitrogen molecules at 0.364 nanometers. Smaller molecules navigate the polymer chain network of vulcanized rubber more easily. Additionally, compressed air contains water vapor that absorbs and releases during temperature changes, creating pressure fluctuations. Aviation adopts nitrogen tire inflation as the standard for commercial aircraft. Military aviation follows. NASA follows for spacecraft launch vehicle support equipment. Formula One follows in the 1970s. Tire performance became the primary competitive differentiator, and inflation stability became critical to maintaining consistent handling. Every performance-critical and safety-critical tire application on Earth switches to nitrogen over a 20-year period from 1956 to 1980. And the application that accounts for 95% of all tires on Earth, the passenger car, remains on compressed air. Not because nitrogen does not improve performance, because the passenger car tire service industry had not yet figured out how to monetize the switch. Now, let me show you exactly why this works. Because the gas permeation physics is straightforward enough to understand in 60 seconds, and devastating enough to make you angry that nobody mentioned it when you bought your last set of tires. Rubber, the material from which tire sidewalls and tread compounds are made, is a polymer. Like all polymers, it is not a solid in the absolute sense. It is a cross-linked molecular network with spaces between the polymer chains through which small molecules can diffuse. This is gas permeation. Every gas that contacts a rubber surface permeates through it to some degree. The rate of permeation depends on two properties: the size of the gas molecule and the solubility of the gas molecule in the rubber polymer. Oxygen has two disadvantages for tire inflation that nitrogen does not. First, oxygen molecules are smaller than nitrogen molecules. At the molecular scale, this size difference matters significantly for permeation through the tight polymer network of vulcanized tire rubber. Oxygen navigates the spaces between polymer chains more easily and escapes the tire faster. Second, and more significantly, oxygen is significantly more soluble in rubber polymer than nitrogen. Solubility drives absorption into the rubber compound, which is the primary pathway by which gas escapes the tire. Oxygen's higher solubility means it is absorbed into and through the rubber wall at a rate approximately 4 times higher than nitrogen under equivalent conditions. This is why air-inflated tires lose pressure faster than nitrogen-inflated tires, even though both gases are at the same starting pressure. The oxygen fraction of compressed air, approximately 21%, escapes the tire at 4 times the rate of the nitrogen fraction. Over weeks and months, the tire effectively leaks its oxygen content out through the rubber wall while retaining most of its nitrogen. Studies published in the journal Rubber Chemistry and Technology have documented tire pressure retention differences between nitrogen and air inflation. Consistently, nitrogen-inflated tires show 60 to 80% better pressure retention over a 30-day period than air-inflated tires. The Tire Industry Association's own technical guidance acknowledges nitrogen's superior pressure retention properties and recommends it for consumers. The recommendation is in their technical documents. It is not in their promotional materials at the tire service counter. Now here is where the story takes the turn the tire industry has always hoped you would never connect. The global tire market generates approximately $200 billion in annual revenue, with the U.S. replacement market alone accounting for $40 billion per year. Every dollar of that replacement revenue is generated when tires wear out. Tire wear rate is directly related to inflation, pressure maintenance. Chronically underinflated tires wear faster, wear unevenly across the tread, and fail structurally sooner than correctly inflated tires. An underinflated tire running at 5 psi below specification wears at approximately 20% faster than a correctly inflated tire. At 10 psi below specification, it wears 30 to 40% faster. Yet, the average driver checks pressure less than once a month. Tires lose 1 psi per month at constant temperatures, with additional pressure loss and cold weather as temperatures drop. Drivers waiting for a warning light are running significantly underinflated for a substantial fraction of the tire's service life. This accelerated wear pattern generates replacement purchases ahead of the schedule that correctly maintained tires would produce. The tire industry has no commercial incentive to promote practices that extend tire life, like regular pressure checks or nitrogen inflation. Nitrogen service is sold as a premium add-on at $5 to $10 per tire, generating significant revenue per vehicle at installation. This pricing positions nitrogen as a specialty service rather than the straightforward atmospheric chemistry it actually represents. The same nitrogen costs approximately $1 per cubic foot from welding supply stores, which is roughly the volume of a passenger tire. Consumers accept premium pricing because the product is associated with aerospace and motorsport, obscuring the availability of the commodity alternative. Understanding these hidden economics allows you to make better maintenance choices and avoid unnecessary costs at the tire shop. But here is what the tire industry's premium positioning cannot suppress. Because the physics is documented in every tire engineering reference, the automotive enthusiast community has been discussing nitrogen tire inflation since the 1990s. And the fleet management community that operates large vehicle fleets has been systematically documenting nitrogen inflation's operational benefits for decades. Commercial truck fleet operators have the most rigorous documentation because a fleet running thousands of tires experiences inflation management costs at insignificant scale. A commercial fleet operator managing 500 trucks documented a nitrogen tire inflation program implemented across the fleet in a 2017 transportation industry publication. Before nitrogen inflation, the fleet's average tire pressure check frequency was every 2 weeks because pressure loss required it. After nitrogen inflation, the check frequency extended to monthly with no increase in underinflation incidents. Tire replacement rates, measured by miles per tire rather than time, improved by 14% across the fleet over a 3-year evaluation period. The improvement corresponded to approximately $180,000 in reduced annual tire replacement cost across the 500 truck fleet. The automotive enthusiast community has documented home nitrogen inflation setups using welding supply nitrogen cylinders for years. A tire enthusiast in Texas documented his home nitrogen inflation system in a 2020 online forum post. He purchased a used 40 cubic foot nitrogen cylinder from a welding supply store for $75 and a regulator for $35. He fills his family's 4 vehicles and 2 motorcycles with nitrogen at home for an annual nitrogen refill cost of approximately $15. His documented tire pressure retention over 6 months shows average pressure loss of less than 1 psi per month across all vehicles. This compares to the 3 to 5 psi per month he had documented with air inflation on the same vehicles before the switch. Total system cost, $110. Annual operating cost, $15. Annual tire service center nitrogen fill cost avoided, approximately $80 to $120 per year. Here is exactly what to do. There are two approaches depending on your situation. The first approach is using your existing tire service relationship, but with complete information. The second approach is the home setup for drivers who want to manage their own inflation permanently. For the tire service approach, next time you have tires serviced, ask specifically for nitrogen inflation rather than compressed air. Most tire dealers offer nitrogen. If they charge more than $5 per tire for the initial fill, that represents reasonable equipment recovery cost. Subsequent top-ups should cost less. If your dealer does not offer nitrogen, any automotive service facility with nitrogen equipment can fill your tires. Ask specifically about their nitrogen purity level. Effective nitrogen tire inflation requires nitrogen purity of at least 93%. Lower purity defeats the purpose because the remaining oxygen continues permeating at the standard rate. For the home approach, purchase a used or new nitrogen cylinder from a welding supply store. A standard 40 cubic foot cylinder costs between $50 and $100 used, or up to $150 new. Purchase a nitrogen regulator with a tire inflation hose attachment. A suitable regulator costs $30 to $50. Total equipment investment in $80 to $200. A 40 cubic foot cylinder fills approximately 40 passenger car tires from empty. At typical usage rates, one cylinder lasts 1 to 3 years before requiring a refill, which costs $15 to $30. Here's the inflation procedure. Deflate each tire completely by pressing the valve core pin to release all existing air. This step is critical. Topping up air-inflated tires with nitrogen does not produce pure nitrogen inflation because residual oxygen remains. For full nitrogen inflation, the tire must be completely deflated first and then filled entirely with nitrogen. Connect your regulator and inflate to the specified pressure shown on the sticker inside the driver's door jamb. Check and record the pressure immediately after filling. For ongoing maintenance, check pressure monthly for the first 3 months. After the retention rate is established, a quarterly pressure check is usually adequate to maintain inflation within 2 psi year-round. Total ongoing annual cost for a household managing 4 tires at home is approximately $15 in nitrogen refills. Compare that to monthly air top-ups and the accelerated tire wear that inconsistent inflation produces across the life of your tires. Some knowledge does not disappear because it failed. It disappears because the industry built on the problem it addresses has structured its revenue model. The Goodyear engineers who switched Boeing 707 aircraft tires to nitrogen in 1956 were not trying to help passenger car owners maintain tire pressure. They were solving an aviation safety problem with the most effective available technology. The motorsport engineers who standardized nitrogen in Formula One tire inflation in the 1970s were not trying to help weekend drivers save money. They were optimizing a competitive performance variable with every available tool. Neither group had any motive to communicate their findings to the passenger car tire industry. The industry had no motive to share findings because they would extend tire service life and reduce replacement revenue. The physics that makes nitrogen superior to air for tire inflation is not a secret held in corporate vaults. It is in every material science curriculum that covers gas permeation through polymer membranes. The oxygen molecule permeating through your tire sidewall right now does not know about the revenue model that depends on it. It is following the concentration gradient from the high pressure interior through the polymer network toward the lower pressure atmosphere outside. The nitrogen molecule has a slightly larger diameter and a lower solubility in rubber polymer. It stays in the tire longer. That is the complete story. The physics is 3 sentences. The industry structure that obscures those sentences is worth $40 billion per year in the United States alone. Think about the tire pressure warning light that comes on every winter, or the tires that wore out faster on one edge. Subscribe and share this with someone who deserves to know the gas keeping their tires inflated costs $1 per cubic foot. The aerospace industry has been buying it since 1956. The next vault opens soon.